Hello, I'm Bram. I work here at Max currently working at a huge insurance company. We have a lot of developers all around the Netherlands, even at the government. So that's about Max a bit. That's where I work right now. My presentation, I'm going to talk about security and privacy. These days we hear a lot about data leaks and security breaches and all the good stuff. So I guess it's important to know for us developers what we should at least know as a minimum about security. So I'm going to tell a bit about history, always good to know. Hashing, what is a salt, what is an HMAC. We're going to do some symmetric cryptography and some asymmetric cryptography. So that's the program. So the history started roughly 2,000 years before Christ already with the Egyptians. Very smart people. There's hieroglyphs on temples that indicate ciphers. So that's quite cool. Then came the Greek, and they had a fun method. I'm not sure if anybody knows what the method was. They used to have slaves, and they shaved their heads of the slaves, and then they would tattoo the message on the head, and then grow the hair back. So that way you conceal a message. Technically it's not crypto, but it's one of the first signs of real crypto. And then came the Romans, and we came with a real first cipher. It was called the Caesar cipher. You can see it on the right. It's a symbol, but it works like you have two rotating disks with all the characters of the alphabet you use, and you can offset those, and then you pretty much have a mapping. So if you have an A which is mapped to a Z, you will type a Z. So that was one of the first real ciphers. Then in the Middle Ages, not much happened. Well, there was a lot happened. There was a lot of development, but they started using math, but most of it didn't work. Crypto analysis started to bloom as well, and 9 out of 10 times the ciphers that were created were not safe. So yeah, that was quite an issue. Then past 1800s, starting with World War I and World War II. That's when crypto really started to be more important. Troops needed to communicate securely. So that's when a lot of development started to work. And then eventually when the computer came, which was very good at math, it all started to work out really well. Then in the future, because already some ciphers we have right now these days are already deprecated because we have very powerful computers that can break them instantly. In the future, we're going to go to quantum computers, which some ciphers we have right now are set to be broken already by quantum computers. So that's the future of crypto. The first thing for crypto, which is very important and plays a big part in anything you do with security, is hashing. What is hashing? Well, it technically comes from the kitchen. It's pretty much chop something up, break something down, put it in a blender, in a kitchen machine, and mash it up. That's actually what hashing is. You put in any amount of data, any bytes, and you simply perform something with it. It can be 1 byte, it can be 1,000 bytes, doesn't matter. It has a deterministic output, which means that if I input the same byte over and over again in a new hash function, it will always output the same hash, which is one of the elements that's very important for hashing. Then it's also important that a hash has a fixed output. So whenever I use a certain hash function, you will see that it will always have 32 bytes of output. For instance, if you use SHA-256, it will always have 32 bytes of output. Doesn't matter what you put in there, if it's a million or 1, it will always have 32 bytes of output, which is very important as well. They also have to be very fast. They are used so often that if it was a very slow algorithm, it wouldn't be useful to have it in your security algorithm. And also, it is irreversible. I put an asterisk there because hypothetically, there are situations where you could determine certain values from a hash function, but it's hypothetically irreversible. So there's no computer yet that really did something with hashing. So that's about hashing. Yeah. So what can we do with a hash? For instance, if I have a database, we'll get to this in a bit. If I have a user database and I want to store their passwords, but I don't want to store the actual passwords because, of course, when my database gets hacked, they can see what the password is. Instead, I can store the hash of a password. So I store the hash of the password, and then when the user logs back in, I recompute the hash, compare the hashes, and then if the hashes match, because it is deterministic output, we can say that the user is logged in. Now, of course, that opposes a risk, and I'll show you. And if I am correct, you are able to join this on your device if you are connected to the network of the guest network of Maxdoro. Feel free to create an account. I'm not going to store any data, but well, feel free to enter anything you want. I'm not sure. I guess. So I'm now logged in. And if I go to the Users tab, because I've listed all the users that are available, you can see that I store the username, which you use to log in, and the password hash of the user. So I've hashed your password that you've entered, and I store that as well. And I can see that there are people here already, Maxdoro and MacGyver, that have the same password. Because the hash of the two is the same. So this password, I can now say that these two persons have the same password. So if I were to hack one of the persons, I'd be able to enter the account of the other. Now, of course, that is a security risk, and we need to fight that. So let's continue the presentation. A way to fight that is not... Oh, yay. One of the slides has gone. There was supposed to be a slide about a salt here. Again, a salt comes from the kitchen. What is a salt? A salt is pretty much something you add to taste to differentiate the output that you create. Same in the kitchen. If your tomato soup is not salt enough, you add salt to make it taste better. The same happens with the hash. Because the output is deterministic, and I can do an analysis based on the hash, we can do lookup tables, we can do rainbow tables, it's important to randomize the output that we get from the hashing of the password. Now, how do you do that? When the user enters the password, we also add the salt that we randomly generate. Then we combine the password and the salt, and we put that in the hash function, which again will create a deterministic output. Then when the user comes back later with the same password and the same salt, which of course I will store in the database, I can then recreate and recompute the hash and compare those. So that way, everything becomes secure, or more secure, I should say. So if I say enable salt, you can now see Maxdoro and MacGyver, which we know have the same password, now have a different value for their stored hashed password. So right now, if I only were to have this table, I could not be sure about the passwords that they have entered. So this is one way to mitigate analysis on password hashes, for instance, which is already something I guess we should know. Assault will come back later as well. In the Symmetric Crypto, where is my screen? Here. So that's a hash and a salt. Shame I missed the page. All right, so a hash is used to check integrity. We can compare data, we can validate a hash if we have the same input. We can recompute the hash and validate that the data we have at a certain point in time is the same as we had previously. But anyone can compute that hash. There's no point, I mean, I can ask person A to compute a hash for some data, and I can ask person B to compute a hash for certain data, but I cannot determine that the hash they've created was created by them. I can only know that at some point they must have gotten the hash, but I'm not even sure if they even had the data. So in comes an HMAC, which is pretty much authenticated hashing. Because what we add to our hash function is a key, which I share with someone. We have a key in common. So person A and person B have the same key. At that point, they can compute a hash function using a key, and only they have the key. So only they can compute that hash function. And I can compare it because I have the key, and I can recompute the HMAC, and they have the key. So next to integrity, we also get authentication, which is very, very useful in some situations. An HMAC is also used in JSON web tokens. Very common on the internet these days when logging in with a username password in an authentication or authorization server. That's about an HMAC. HMAC is just one example. There are multiple other MAC message authentication codes available. There's also a CMAC, which is almost never used. Then there's a GMAC, which is used in symmetric encryption when using IS in GCM mode. And then there's also a poly 1305, which can be used in several modes, which is technically also a MAC, which we'll get to in the next slide almost. So the HMAC at work, let's see. There's this nice tool. I can compute an HMAC. So let's give in a message. Let's say hello world, because why not? And as a password, a password in this scenario is the key. I'll enter admin, and then I can compute the HMAC for this value. So say I want to use the SHA-256 variant of that, and I want to verify it. The HMAC we computed was this value. The password was admin, and the hash algorithm we used was SHA-256. If I now were to verify it, all works out. The same key, the same original data, and the same MAC. If I were to change the data to verify, you'll see, oh, I need to, with the correct password, and that's a nice pop-up. You can see that the HMAC could not be verified because the data, the original data, has changed. So the message authentication code is no longer valid. The same will happen if we do enter the same data, but change the password. Because the user doesn't have the key to create the message authentication code, so it will fail. It will not compare, it will not be the same. So that's an HMAC. Where is the mouse? There it goes. So authenticated hashing, pretty much. Then we go to encryption, which tends to be very tough and difficult, but it's actually not. Encryption is pretty much we share a key, we have the same key, and we compute something with it, and that's encrypted. And the cool thing is, if you have a key, you can also undo the compute, and you have the original data. So it's reversible. Encryption versus decryption. So the encryption is creating readable text into unreadable text or protected data, and decryption is reversing that. We talk about a ciphertext and a plaintext. Ciphertext is encrypted data, and the plaintext is unencrypted data. That's pretty much encryption. Then a very important step, which is usually missed by a lot of people, is again some kind of salt, which is in symmetric encryption usually called a random, an IV or an initialization vector, or a nonce, a number only used once. This again, usually we encrypt data which is not different between sessions. Say I want to encrypt the user password. The user's password is not going to change each session they log in. So technically, if I were to use the same key and the same password each time I encrypt, I will get the same output ciphertext. So to prevent that, again, we add the salt we saw earlier, in this case the random or an IV. Now, one of the things I do want to point out, which is a common mistake when doing symmetric encryption, is that people reuse the same IV and the same key. And that technically is the same as before with the hash. no data is changed, so the output data is not different than before. So it's very important that if you do any encryption on any platform, but mainly on iOS, it is very important that you randomize your random or your IV. If we're going to use CryptoKit, it does this automatically for you, but you can also do it yourself. But this is very, very important. Symmetrical encryption is also very difficult for some people because there's so many types. There's IS, there's DES, there's triple DES, there's so many standards. But try to stick to a standard. Apple provides a couple ones, do some research. IS and Cha-Cha are very decent common ciphers that we can use these days. Now most of these ciphers, especially IS, is known for their modes, which is pretty much how are you going to use the cipher. There's a way to use certain algorithms in a specific way where they append ciphertext and XOR certain blocks and they use the key in a different way. That's called a mode. And that is very important to know because if you abuse a mode, you can get something like on the image. The original image is the penguin of Linux, and we can encrypt that using ECB. And ECB is known for simply performing the same operation over and over and over again. And you can see that the resulting image, of course, it is encrypted, the color is gone, but we can clearly see what the original image was about. It's still a penguin. If you use something else than ECB, you can see that we get more or less a random output. So it's very important to know which mode does what and when to use something. Not using the correct mode is, of course, a security risk. Then there's also IIS, which I talked about, that is a block cipher. And then there's also Cha-Cha 20, when we're talking about iOS, this is of course, which is a stream cipher. The difference between the two is that a block cipher operates on chunks of bits. For IIS, that's 16 bytes, if I recall correctly. And a stream cipher operates byte by byte. So it does one at a time. Both of the IIS and Cha-Cha variants are authenticated ciphers, which means you can also add extra data which you want to be authenticated. So think of this, the MAC function we had before, the GMAC and the poly 1305, which we mentioned before. They are added to your final output. So there's extra authentication in your end result, in your ciphertext. Another cool thing to note is that on iOS, IIS is hardware accelerated. So it's preferred usually to use that one. But Cha-Cha is very decent for small amounts of data. Currently, I've implemented everything on the server that we just saw using CryptoKit, which only supports IIS GCM. And it doesn't look like Apple is going to support anything else but that. But if you do want to use older versions of IIS, you can use the Common Crypto library. It's not preferred. There's an old C-like language syntax, which is kind of odd to use, and it's very, very error prone. So just keep that in mind. We can show something about the symmetric encryption. There's a messages tab, which again you can open and you can send messages to me. I'm logged in as root at the moment, and we can send each other a message. So say I were to send, what's your name, if I may ask?
Matthijs, but my name is Henk too, I think.
Okay. There you go. Let's say I'm going to say, send you a message, and we'll pre-share a key. Our key, again, is going to be admin, just because this is a demo. And I'm going to send you the message. And if you were to send me a message,
I did.
Great, so I got a message, and I want to open this.
Password is admin.
Admin, right. So the message is protected using symmetric encryption, IIS GCM, and I need the password to open the message. So only if I have the correct password will I then be able to see the message. Now, of course, this works pretty nice. If I enter the incorrect password, we will see that the message won't open. Password is incorrect. Technically, this is a secure WhatsApp environment. The only downside here is that every time we send a message, we need to say what our password is, what our key is. Of course, for now, we're 2 meters apart, that's fine. But if he were to go home and I were to go home, we couldn't do that anymore. So this works, but it's not very useful. So there were a couple of guys that were way smarter than I am, and they thought about it, and they had the same problem. And they were like, we need to do something about that. And in came asymmetric crypto. What's so important about asymmetric crypto? The key, pretty much. Your key using asymmetric crypto exists of 2 parts, a private part and a public part. And the private part is very important, especially the private. That's your key, and you should never share it. PlayStation once did, and they had a lot of problems with that. All of a sudden, people were able to download games on their PlayStation, which they were not supposed to do. But the public key, you can leave that anywhere, doesn't really matter, but preferably share it with a party you want to communicate with. The cool thing is, using these keys, we can create a secure channel to communicate. So we don't need to share the key. I need your public key and my private key, and we can create a secure message. I again created this with CryptoKit. Some of you might have heard of RSA. RSA is one of the algorithms used in asymmetric crypto. It is currently not supported in CryptoKit. It might be in the future, but they're not sure. One of the downside of RSA keys is that they are very slow. Not only in creating them, they require lots of random data to be created, but they're also slow in using them. RSA keys can still encrypt. We'll get to that later. Not all asymmetric crypto can encrypt, but it's very limited, it's very slow, it's not really nice to use. So we needed something else. So not only RSA is there for asymmetric crypto, we also have elliptic curve crypto. And elliptic curve crypto has some benefits. The key is much smaller, 32 bytes roughly, usually. There's certain bigger ones, but that's a lot faster to create. ECC is also very fast compared to RSA. ECC is also supported in CryptoKit, which is also a if you want to use iOS CryptoKit. So yeah. Another thing to note about ECC, because that's what we're going to use in the next demo, is it has certain curves. And a curve is pretty much variables that define how the key works and what it is capable of. iOS supports 4 using CryptoKit. The P256, P384, and P521, and then there is, which I consider the most secure, curve 25519, which is the 4 curves that iOS supports. I don't want you to remember this. Just know that there are different curves, they function the same, they don't communicate with each other. That's all there is to it. There is a big critique on the curves. Some of them are created by the NSA or CIA, so some people are like, I don't trust that curve, so something to consider. So asymmetric crypto, what does the key actually do? So your private key, which you should never share with anyone, is capable technically of signing and decrypting messages. Signing is pretty much creating an HMAC with your asymmetric key. You can compare, it's not the same, but you can compare the two. And decrypting is, of course, performing a decrypt operation like symmetric crypto. The public key, on the other hand, can verify. So if I have a signature, some original data, and a public key, I can verify that that signature, original data, and key belong to each other. And it can also encrypt. So if I know someone's public key, I can encrypt using that public key, give the ciphertext to that person, and only that person can decrypt using the private key. So that's very cool about this. I gotta tell you that elliptic curves don't support encryption and decryption. That's also a downside of elliptic curves, but they are very fast and they are capable of doing other things. But this is very important. Private key, the signing, decrypting, public key, verifying, encrypting. So elliptic curves and also RSA. Elliptic curves cannot encrypt or decrypt, but what can they do? Well, they can be used to exchange keys. So on the image, on the left side Bob, on the right side Alice. Bob has a private key. Bob can see Alice's public key. He can then combine the two in an algorithm called an exchange algorithm, and it can create a symmetric shared key. Now the cool thing is we can do this the other way around as well. So if Alice can see Bob's public key with her private key, she can then combine the two, and they will output the same key. So the key you see down here is the same key you see down here, which is amazing, pretty much. This way, we don't need to know each other's key on forehand, like we just did. We shared the admin password, but we can share each other's public key, and we can then compute a key which we can use to symmetrically protect data. This is very cool. During the exchange, we also use a key derivation function to increase security, strength, and randomness of the key. It is very important to do key derivation. Don't miss this step if you do exchanging. The CryptoKit provides decent algorithms to do this, but it's very important. There's also something called forward secrecy. Right now, if we create this symmetric key together, we then can keep our private and public key still with us. But technically, if we were to use them again, the same output will be given after exchange. Now, of course, that can be an issue. So if, for instance, HTTPS uses this system as well, it wouldn't be secure, because if someone at some point were to break the crypto or capture my private key, they could then log and see everything I ever did with that key, and they can still see my HTTPS traffic. So forward secrecy relies on the fact that you create the public and private key, use them once, and then throw them away. So it's pretty much a key used only once. So then you have forward secrecy. Then there's called MITM, which is known as a man-in-the-middle attack. Not doing proper asymmetric crypto or not having anything that validates keys from another can cause attacks called man-in-the-middle attacks. So I simply I'm not going to go into detail what that is. Most of you might have heard of it, but it's a very big risk when doing asymmetric crypto. There is a way to counter that. HTTPS is secure after all. That's creating a trust anchor, something that we know we can trust, something that we believe is truthful and secure. And a certificate authority where we get our HTTPS certificates is one of those trust anchors. Yeah, so let's do the same demo with the message, but now instead of sharing the password, we can simply go to the messages v2. I have no message here. And if I now were to send a message to Henk again, let's make it English. Hello again. You can see I don't need to enter any passwords. The server will, because the server by luck knows both private keys, because this is a demo after all. It can perform the exchange underwater, and it will encrypt using the generated secret key. And I can simply send in the message, and I don't need to share any password. There's simply a secure channel without us ever needing to share anything. So the same here. I can simply decrypt it because I have used my private key to decrypt that message. Now this is what my keys look like. I've created two, one for signing, one for key exchange. We can then, for instance, sign something with my private key. Let's say hello world, because we are also developers. This is a signature created with my private key for that data. If I were to copy this and go to verify, I can then verify that the signature that was created for that data is correct. And if I were to alter the data, you can see the signature is no longer valid. The same happens if I were to change the signature data. So instead of making that an E, make that an F. Even then, the signature is invalid. So this is also a way to add authentication to data if you know keys from one another. So yeah, that's very useful. And we use it every day using our secure HTTPS traffic. To sum up, we talked about hashing, which is integrity checking of data into a fixed output size, and it's irreversible. We also talked about salt, which is adding randomness to deterministic output, and a way to protect and safeguard against common attacks. We also talked about an HMAC, which is authenticated hashing, I'd say. Use a key to create a secure value. Then, of course, symmetric encryption, AES, ChaCha, protect data in a reversible way if we know the key. And then also asymmetric crypto, which is also, again, used to integrity check using a key. Also, of course, create a secure session or a secure channel without predetermining keys or as a relation or a channel, which is, of course, the underlying method for HTTPS. Are there any questions related to security?
What does HMAC stand for?
Say again?
What does HMAC stand for?
Hash-based message authentication code. Well, if there are no questions, I can only say, if you ever want to do anything with crypto whatsoever, please check out the documentation. Apple CryptoKit is actually pretty decent. Documentation of Apple is actually pretty decent at all. There's also an open source version of what Apple delivers. It's created for Linux, and check it out. I've created the server using Vapor, so I do want to mention them. If you want to use a web server in Swift, simply check them out once. It's fun. And then if you want to do something else with crypto, which is very elaborate, very easy to get to with Python, go to cryptography.io. They've implemented nearly any cryptography algorithm, anything you know about it. So if you want to want to mess with it, want to learn, definitely go there. That was it.